All right, everybody, this is section 2, properties of water. So in section 1, we talked about the atom, we talked about elements, compounds, molecules, and one we kept hitting on was, one molecule we kept hitting on was H2O. Remember, that is water. Water is necessary for life on Earth. In this section, it's fairly brief. It covers a lot of the things that you did in your reader last week, 2.2 reader. And we had the 2 short answers. So here are your slides. We're going to fly through them pretty quickly. Shouldn't take us long. And that way you can get to your quiz with section 2. All right. So you want to write these down on your class notes, open it up in Cami, and then fill in the blanks where necessary. You can click back and forth to do that. So without getting too much into it, because this is really chemistry, there's these special features in water called hydrogen bonds. We can see right here a regular H2O molecule. We can see that positive and negative parts of the oxygen and hydrogen hold it together. But then we also see that this end of the water molecule itself is positive, and it is drawn to the negative side of that water molecule. It's a pretty special feature in water. Basically, they're polar is what it's called, and these hydrogen bonds pull these water molecules together. All right. Again, what we just said, the hydrogen bonds form because the slightly positive hydrogen atoms and slightly negative atoms, all in these water molecules. That's not the super important thing I want you to see. These 3 properties of water that come from these hydrogen bonds is what makes water really unique. The first property is high specific heat. High specific heat. What this means is water doesn't want to change from a liquid state. It tries its best to stay a liquid. Of course, we know the other 2 states found naturally here on Earth is gas and solids. Water wants to be a liquid. What do we call water when it's a solid? Ice, that's right. What do we call water when it's a gas? Water vapor, correct, or steam, you might call it that. But high specific heat means it wants to stay water. A logical person would go, okay, it hits 32 degrees Fahrenheit, that's the freezing point of water. All water that's at that temperature just automatically freezes over. No, it doesn't do it quite like that. Yes, some does. Think about a good example would be if you've ever been somewhere really cold, or you've maybe watched a movie or a TV show with a frozen like pond or a frozen lake. That top surface is very frozen, right? People could ice skate on it. In some situations, you could even drive a vehicle on top of the lake. But then you might see somebody go out there with a saw or something and throw a fishing line down through the ice, and they can catch fish in that liquid water underneath the ice. Okay, high specific heat is the reason that whole lake doesn't just immediately freeze. Yes, that top cap of ice does give it some insulation, but that water underneath can be right around 32 degrees Fahrenheit or 0 degrees Celsius, which is the freezing point of water. But it wants to resist that. It tries its best not to freeze over. It wants to stay liquid. Think about why that's important. Think about plants, trees that exist in cold climates. There's water going up through the trunk of a tree. Okay, it may be small amounts, but it's going to go up from the roots up to the branches and the leaves and whatever else is growing on them branches. If that water reaches a certain temperature, 32 degrees Fahrenheit, or actually well below that, it will freeze up, causing that tree to start cracking, that water inside freezing up. And so the high specific heat is what keeps that from doing that change of state, right? Same principle, high specific heat. Think about boiling a pot of water. If you put on like spaghetti or something like that on the stove, you'll throw a pot of water, you'll turn on the eye first, and that eye gets really, really hot. It could be 300, 400 degrees Fahrenheit, and kind of put your hand over near it. You know how warm it is. You put that pot of water on the eye, that pot starts heating up. In fact, if you reach and touch the pot, not like the handle, your hand may get a little burn. Meanwhile, the water is still not boiling. Once again, a logical mind would go, okay, once it hits the boiling point of water where it's going to change from a liquid state to a solid state, boom, it's it. But no, it doesn't do it like that. It takes a lot more. You can sit there and watch it. You might see a few bubbles right at the bottom of the pan for a little bit, And then eventually you'll see those bubbles start popping up, and soon you'll have a roar and boil, but the whole pot doesn't just disappear automatically. Even though the water inside of it has reached the boiling point, it's still taking a lot to turn into that steam or that water vapor, and that is high specific heat. Okay, that's an important property of water. We like water to be liquid because it's usable for living things in a liquid state. Second property of water is cohesion. You read about this. Cohesion is the attraction between molecules of the same substance. Okay, dealing with water, because of those hydrogen bonds, it becomes very cohesive. It wants to stick together, and there we see that that prefix co. Okay, co means together. Co means together. Cooperate, coordination. Okay, so that kind of helps you remember it. You want to cooperate. There want to be coordination on your cheerleading squad. That means everybody's on the same page, right? So cohesion means same substance molecules sticking together. I got a video for that. Let's play it. How many drops of water do you think could fit on this penny? A logical person would go, well, this liquid water is just going to hit the penny and then flow off. It hit right here. This must be, frozen frame, and then it falls off. So make a prediction. How many drops of penny do you think would be on there? 3, 6, 10?
Welcome back to Kids Fun Science. My name's Ken. Today's experiment is surface tension. Drops of water on a penny. As always, no supervision is required. What you need for this experiment is a penny, a pipette, or an eyedropper, and dish soap. So now you make a prediction on how many drops of water I'm able to put on top of one penny. The object of this experiment is to see how many drops of water.
Oh, no. Sorry about that, everybody. I was cranking up the speed.
Welcome back to Kids Fun Science. My name's Ken. Today's experiment. Hydrogen bonds are formed by the hydrogen atoms in one molecule being attracted to the oxygen atoms in another molecule. The cohesion of the surface tension of the water becomes apparent when the drops of water you add to each penny reach the end of the penny. Once the water
So sorry about that. I clicked on it too soon. Got a little crazy. What you saw was that it started popping up in that dome shape. It almost looked like a Jello mold somebody might bring to Christmas dinner. But that water, that cohesion between those hydrogen bonds, causes it to start bubbling up instead of spilling over. The water wants to stick together. It's defying falling off that penny in order to stay together. Okay, so we got 2 of the 3 properties already. One's high specific heat. One is cohesion. The third special property of water is adhesion. This is an attraction between different substances, namely water. It's when water wants to stick to other things. Okay, water wants to stick to other things. You have a good example of this if you take a shower. You might turn off the shower, get through, and look around, and there's probably little water droplets, beads of water on the shower walls or the shower curtain. And that water, it isn't specially sticky or anything. You just took a shower with it. You know that. But it's wanting to adhere to those things. It is defying gravity. Gravity, of course, trying to pull it down, but it's fighting against it and staying up there. And it may stay up there for hours until it evaporates or until it falls down and gives into gravity. But it kind of hangs there. Adhesion, it wants to adhere to it. It wants to stick to other things. We got another video here. They are some low-talking people. So I'm going to just tell you kind of what's going on as we speed through it. What am I doing here? Playback speed. All right. Oh, goodness me, guys. Sorry. All right. So they're going to do an experiment. There's 3 beakers. 2 on the sides have water. The one in the middle, of course, doesn't. She's going to put blue food coloring in this one and give it a nice stir. She's going to put yellow food coloring in the other one and give it a good stir. Going back to first grade, you probably remember, what does blue and yellow make when it mixes? Green, of course. So now she's telling us she's taking 2 rectangular paper towels, going to stick one in either water and then the other one in the middle. Okay, she's going to this is going to show us how adhesion works. Notice how the blue and the yellow are both creeping up over the napkin. And look how it starts to fill up. And then a couple hours later, you see the finished product. You see more green than you had of the other substances. Okay, and now they're being all cutesy. So adhesion, we see how that works there. It's not just these paper towels being super absorbent. Okay, these water molecules from either of the side jars is adhering to the paper towel and moving over into the other jar. So again, you see it defying gravity, going upwards, and then it goes over and fills up that middle jar. Water wants to adhere to other things. We see this in nature, how any plants that are tall, even if it's a flower outside, or I say tall, just got any height to it at all. Think about a flower, how the water gets from the roots, it goes up the stem. There's no straw sucking at the top of the stem to make water move up. Instead, it's adhering to the sides of that stem and moving its way up to the leaves and the flowers. Okay, so this water adheres, this adhesion, this property of water is what makes it do that. So there's the three special properties. Let's fly through this real quick. Many compounds dissolve in water. Water is a good thing to dissolve other things in. A solution is formed when one substance dissolves in another. We call a solution a homogeneous mixture, and that's because it's not easily separated. Think about a Kool-Aid. You mix up some Kool-Aid mix, say it's with sugar in it. We can stir that up in a glass of water. You can't really separate the two. Okay, it's homogeneous. It's mixed throughout. Okay, that's what a solution is. A solution has two parts. One's called a solvent and one's called a solute. The solvent is what dissolves other substances. Think of salt water. Okay, salt water is nothing more than salt dissolved in the water. Okay, but the solvent in this case is water. There's more of it for one thing, and secondly, it does the dissolving. Salt water in the end has more characteristics of regular water than regular salt, right? We know it's a liquid. Yes, it's got a very salty texture, but it's more like the solvent in the first case. The solute, of course, in salt water is what is being dissolved, and that is the salt. Okay, not just salt water, lots of other things can dissolve in water. So water is usually the solvent because it's so good. Lots of things can be solutes and dissolve in the solvent. The last thing I want to talk to you about is something called the pH level, the pH scale. Without getting too much into it, just wanted you to see that the pH scale goes from 0 to 14, okay? Normally when we think of scales, we think about like a bathroom scale. You step on it, it weighs you, 1 being the lowest, and it goes up like 350 or something and being the highest. The pH scale is a little different, okay? Middle is 7. Middle is 7, and the middle is pure water. Water is called neutral, okay? It's not really an acid or a base. We can see that anything less than 7, a pH less than 7, is what's referred to as an acid. You probably heard a lot of things that are acids. Lemon juice, battery acid, stomach acid, all these different things are acids. They have a pH less than 7. We won't get into the chemistry of it. Like I said, the main thing I want you to know is 7 is the middle. It is neutral, okay, and it is pure water. Anything greater than 7 on the pH scale from 8 to 14 is known as a base. It's known as a base. So less than 7 is an acid, higher than 7 is a base, and of course, put a star by it. Water is a neutral solution, and that's a good thing because that means lots of things can dissolve in water. It's not going to have a negative effect on anything like some acids will and some bases will. I gave you this last little chart just to show you, a lot of these things. Pure water is 7. Your blood is actually a little more basic than neutral, 7.3 to 7.5. We see things on the basic scale, things like bleach and milk, and all the way up to things like hair maneuver and household ammonia. So things that aren't very good. And then we go up down towards the acid side, and these are 0s to 6s, or 0 to 6.9s actually. We see things like urine and coffee and lemon juice, like we said earlier, vinegar, hydrochloric acid, stuff that can be very, very harmful. Like I said, the biggest thing I want you to know is 7. 7 is the middle, it's neutral, and water is a neutral solution. So to recap this whole thing, there's 3 properties of water. Special properties: high specific heat, cohesion, and adhesion. A solution is simply a mixture that's mixed throughout. Solvents are the ones that do the dissolving, and solutes are the ones that are dissolved. And then, of course, 7 on the pH scale is water, and water is a neutral solution. I hope this helped. Hope this got your notes filled in. Thanks.